I want to,
they'll
to
switch
move.
it for you.
You switch it? Okay, let's start. We need. I just want to remind you that we have 15 minutes for each talk, so let's try to finish it in something like 12 minutes, and then we'll have some time for questions. So the first talk will be scalable and programmable and dense, the open source RISC-V multi-core with shared resources. So let's welcome Dustin Richmond from South California University. Thank you.
Great, thank you. My name is Dustin Richmond. I'm here today to tell you how you yourself can build a scalable, programmable, and dense Manycore, and introduce the Hammerblade open source RISC-V Manycore. Now, it is well known in computer architecture that modern algorithms are increasingly demanding flexible architectures. They demonstrate diverse communication patterns, novel data types that haven't been seen until the last 5 to 10 years, and data-dependent irregular accesses. Furthermore, they're increasingly demonstrating time-dependent behavior. Now, our goal as a community has been to develop a perfect, scalable, programmable, general-purpose parallel architecture. Has anybody run across these in their research? I don't see many raised hands. Now, we think this is an unrealistic goal. No static architecture can achieve perfection. So, what if we consider this problem differently? What if what we need is an architecture that is dynamic and can be rapidly customizable at design time, but still provide a relatively good or high-performance base level of performance to many applications? Then we could quickly customize that architecture to provide high performance on each application as they are discovered. This is what we call an agile or a hardware design agile architecture, something that is scalable, programmable, and dense, but that we can rapidly customize. And this is the genesis of the Hammerblade Manycore project. Now, it is also well known in computer architecture that Manycores, yes, are designed agile and parallel, but are they actually scalable, programmable, and dense? In the Hammerblade project, we have demonstrated that we can tape out over 100,000 cores in a 3-nanometer node. These individual cores provide flexible parallelism because they can do branches and all the other irregular memory accesses that are demonstrated in modern applications. And we can facilitate agile hardware design. It requires minimal design teams, as we have at the University of Washington, to go from idea conception to actual implementation. But as historically known, many cores have limited general purpose utility. And this is in part due to several reasons, which I'm going to go into today, but part of it is the kitchen sink mentality that's been in many cores in the historical literature. That is throwing every single feature that could be potentially used instead of considering how do we provide the most scalable, programmable, and dense architecture. And this has forced designers historically to pick between 2 of the 3 best options: scalability, programmability, or density. So how do we architect a scalable, programmable, and dense Manycore? To understand this question, we've developed a taxonomy in our paper between flat Manycores, which have arranged cores in a 2-dimensional matrix and simply scale a number of cores, and hierarchical Manycores, which aggregate cores into neighborhoods that then communicate over a hierarchical network. We develop a third type of Manycore, which is cellular Manycore, which I'll develop in just a second. But first, how do we evaluate? Can you guys please stop talking? How do we evaluate scalable, programmable, and dense? Well, dense is obvious. It's the number of things per unit area. Programmable, in our definition, is the algorithm that facilitates the most, or the architecture that facilitates the most performant of expression of parallel algorithms, not the opposite way around. Now, finally, how do we evaluate scalable? And our definition of scalable demonstrates from historical literature on Manycores, which is just taking a single core and replicating that core until infinity. What we actually focus on is logically scalable. That is, the latency of basic operations are controlled as the number of cores and number of cooperating cores grows. Now, our evaluation of this will be to demonstrate the performance of 10 diverse applications as the number of cells in our architecture increases. Now, that leaves the obvious question, what are cells? This is the root concept of the hammer blade Manycore. We take a cellular approach to attaining Manycore scalability, programmability, and density, or SP and D. We developed the concept of cellular encapsulation, which is the concept where we create these cells with hyperdense cores that have low latency accesses to nearby cache banks. This low latency access allows us to eliminate many of the features that you would see in modern multi-core and other Manycore processors in a process known as cell-driven densification. Finally, we replicate these cells in what is known as cellular uniformity over a uniform network and partition global address space. The hammer-blade Manycore demonstrates these concepts. We have a two-dimensional cellular matrix of cells. These cells contain compute cores and cache banks that are interconnected over a low latency, high throughput cellular network. The caches are also tiled and are operated on by the hyperdense RISC-V compute cores inside of the architecture. In our experiments, we have demonstrated that in a 3 nanometer process, we estimate that we could achieve a 4,500 square micron area and achieve 100,000 cores in a GPU-sized die. Onto cellular encapsulation. Now, one of the key ideas behind the cellular architecture is we should create low diameter cells, not cores, that contain everything to execute a parallel application. This is in contrast to flat Manycores, which have historically included many features inside of each core to run applications such as Linux. Or hierarchical Manycores, which contain neighborhoods of cores, but then have to talk to an L1 or L2 cache in order to perform an application. And these L2 caches are not included in the neighborhood themselves. In contrast, in our cellular architecture, the caches provide everything that is needed to execute the application. And the cores simply perform the operations. The benefit of this is we can eliminate private caches with low latency communication interfaces between the cores and the caches, and also perform efficient word-wise communication for sparse and irregular applications. Now, creating cells will give you good performance, but there is additional work needed to provide low latency and high throughput. And one of the key concepts that we develop in this paper and in related work is the concept of ruching, harvesting unused wires for throughput. Now, it is well known that two-dimensional mesh networks underutilize VLSI wiring, but they are very easy to design and fabricate. You can create a single core, run the wires to the edge of the core, and then stamp out the core to create your architecture. However, in addition to being underutilizing VLSI wiring, they're highly susceptible to congestion under load. So what can we do? In ruching, we decrease the diameter and increase the throughput of our networks by adding additional skip links. Now, the related work that we've shown here at the bottom of the slide will give you more insight into how we design these mesh networks, but they add no design complexity versus a mesh network and substantially increase our throughput under congestion. Furthermore, we can also scale our wire utilization to 100% both in X and Y directions. Now, this ruching is key to the hammer blade architecture, but we add one additional concept that allows us to scale to greater architecture sizes. To demonstrate this concept, we've developed an experiment. On the y-axis, we have 10 different applications implemented on the hammer blade architecture. On the y-axis, we have the bandwidth utilization of each application in the architecture. And you can see how each application is split between non-stalled bandwidth and stalled bandwidth. As you can see, many of the applications have substantial time where they spent stalled in the network. If we add the ruch network, this decreases substantially. However, many applications still demonstrate stalling in the network. And when we studied these applications, we realized that they were actually making sequential accesses to the cache. And what we added is this feature which we call load compression, which recognizes that when sequential addresses are being accessed and compresses that into a single packet that then gets sent to the caches to produce multiple responses. This allows us to provide high throughput and low latency in our network, even under heavy load conditions. This is key for the next concept, which we call cellular densification. The idea here is that we should select features that provide performance and programmability with minimal area in order to maximize density. Now, this low latency is key because it allows us to eliminate many of the features that you would have seen in prior architectures, such as L1 caches or L2 caches or TLB misses. By eliminating these, we can provide a hyper-dense hammer blade core that, as I said before, we believe we can achieve 100,000 cores in a 3 nanometer process. Now, if you're interested in all the features that we added and removed in our architecture, I encourage you to read the paper because there's not enough time to go into all the features that I've shown here. With this implementation, we are able to achieve a 3x improvement in core density and a 1.5x improvement in FPU density versus prior work. Now, you notice that Celerity actually demonstrates improved core density over us, but they did not integrate the Roosh network or the floating point units. So we actually don't consider this a fair comparison. Now, finally, onto the final piece of the hammer blade architecture. And this is the idea of replicating the cells in a uniform global network. And the key idea here is that we can replicate these cells to create both a uniform global network, but also our global address space, partitioned global address space. And this is in contrast to flat mini-cores, which simply have a global flat hierarchy, and hierarchical mini-cores, which communicate between neighborhoods over this hierarchical network. This reduces the performance on sparse workloads because it is well known that aggregated networks don't transmit sparse data efficiently. Now, I don't have time to go into the partitioned address space here, but our partitioned address space allows us to right-size memory allocations so that we can provide low latency to any type of data structure in the architecture. If you're interested in these details, I encourage you to read the paper again. Now, finally, how do we demonstrate scalability? Well, we have two experiments. In the first experiment, we take hammer blade and we create an 8x8 architecture with 32 by 8 cells, so 32 by cores wide and 8 cores high. And we estimate, based on our tape-out validated RTL with 2048 RISC-V cores, that this architecture would run at 1.35 gigahertz. This architecture provides 192 megabytes of on-chip storage with HBM2 running at 1.0 gigahertz. Again, we estimate that this would be a 620 millimeter squared area, which is approximately equivalent to a GPU die in a 1614 nanometer area. We then compare this to a hierarchical mini-core and a density network normalized comparison at a 1416 nanometer node. What we demonstrated is shown on this graph. On the x-axis, we have the applications, which are then compared between the two architectures. We then normalize the runtime to hammer blade. Now, the important takeaway from this graph is that hammer blade performs at least as good as the contemporary mini-core. But there's an interesting thing you can see here. We split the execution time, and we split the total time into execution time and transfer time. And on particularly sparse benchmarks, hammer blade outperforms the contemporary architecture because its ability to transfer sparse data efficiently. We also compare it to a flat mini-core baseline using the feature evaluation that we performed in the densification experiment. And in these experiments, we demonstrate a 5.2x performance improvement over the baseline architecture. Now, I hope I've convinced you in this very brief talk that hammer blade is scalable, programmable, and dense. And the key idea that we've used is a cellular mini-core replicate, which demonstrates replicated cells within a uniform global address space and network. If you have more questions, I'll be around today and happy to take more questions now.
Thank you for the fantastic talk. Questions?
There should be a microphone walking around.
Yeah.
Okay. I think they may want the questions recorded.
Okay. Shai from Google. Do you need to change the code in order to use these cells?
We write in C, so, changing the code.
You have an application, there's 2 billion lines of code in the Google source code base. Yeah. If we suddenly decided, hey, we want to deploy these things, do we need to change the code?
We have found that the major code changes that we need to do are focusing on loop unrolling. We can use a lot of GPU-like code. Our language bears a lot of similarity to common 4-letter languages that use for GPUs. But the main focus is on how do we enable the compiler to perform transformations that let us expose memory level parallelism. in the architecture. So yes, you do need to change the code, but it's not as drastic as you would expect. I'm happy to show you some examples offline.
Okay.
Freddie from Library University. I wanted to ask about the routers. Is this something that you need to program, or it's like a sort of an algorithmic routing? And what is different between the L1 and the L2?
We don't have an L1 or L2. We have a scratch pad, and that goes to the last level.
I think you mentioned L1 router, or maybe I misunderstood, but for the router itself, is it like an algorithmic mapping, or you need to program like a routing table or something?
We don't need to program a routing table. It's static dimension ordered routing, so it goes X, then Y, and then Y, then X on the return path. We don't have L2 routers. That's all one uniform global mesh with an L, push one router.
Luca Carloni, Columbia University. Thank you very much. Very interesting talk. Can you please elaborate on the results that you present across the application? What is the, I guess, an average or the maximum workload footprint in terms of memory, external memory?
Sorry, I didn't completely hear the question.
So you present a result on a variety of applications.
Yeah.
What is the footprint in memory of this application? Which data set? And what's the impact of the transfer from essentially DRAM from outside your engine?
The maximum footprint, I don't remember off the top of my head, but I believe it sort of varies from applications. Some applications generate a lot of sort of allocation, and that's, I believe, the biggest one is sparse matrix multiply, because you can do enormous matrices. But the biggest ones were several gigabytes, and we're using BFS, or graph-based algorithms. Does that get close enough to the question? Okay.
So I guess the natural follow-up is, because you have a claim of scalability, what is that eventually limits your scalability? Is that the communication with external memory, or issues with the internal network on chip, or the ratio between the local memory and the computation?
Yeah, mostly communication between the cells and network on chip, but happy to talk more offline. Yes.
So, the next talk is called Hadass, and other system distributed transaction in age of fast network and SmartNIC. So, you will present yourself, since I didn't get any further information.
Oh, hi, my name is Kokolis. I'll present Reidys, hardware-assisted distributed transactions in the age of fast networks and SmartNICs. So today, we see an unprecedented increase in user data, and distributed systems must split this data across multiple different nodes because it's too costly and inefficient to replicate the data to all nodes. So systems leverage RDMA and RPCs to communicate between the different nodes, and we've seen great enhancements in RDMA with sub-microsecond latency, very high bandwidth, some support for atomic operations, and programmable NICs that can perform some computation. So in such environments, distributed transactions are very popular because they provide acid semantics, so they give the illusion to the user that you are executing atomically. And having serializable transactions simplify how we can reason about distributed applications. On the user side, they always require very low latency. So the challenge here is how to handle the increasing inefficiency of software in distributed transactions. And we come up with this proposal of let's have hardware support for efficient distributed transactions. So in this paper, we analyze the main sources of overhead in state-of-the-art distributed transactional systems and propose hardware that can eliminate this software overhead and devise two new protocols, Reidys and hybrid Reidys, where in Reidys, both local and remote operations of transactions will be executed in hardware, while in hybrid Reidys, only remote operations of these transactions will be executed in hardware. So let's see how a software protocol works first. Typically, software protocols have three phases: the execution phase, the validation phase, and the commit phase. So if there is a transaction, like the one on the top right that is executing on the coordinator node, it can be touching local and remote record to read or write them. Sorry about that. Okay, sorry. Local reads can be performed locally by just reading the record from local memory, and then store the record with some metadata in a software-defined data structure that we call the read set. Remote reads have to issue an RDMA request to the remote node, fetch the record, and also store some metadata for this record in the read set as well. For writes, if they are local, they can just fetch the record from local memory and store it in a software-defined data structure that we call the write set, alongside some metadata until the transaction commit time. And for remote writes, we still have to fetch the record from the remote node and store it in the write set until the commit. During validation, all the records that were written during the transaction have to be logged so that no other transaction can read or write these records during the validation time. And then we have to make sure that there is no conflict between different transactions. And this is happening by rereading all the records that were read during the execution phase and checking whether the version of this record is the same as the version that we had read during the execution phase. If it is, it means no other write happened during this time. Otherwise, we have to squash and re-execute the transaction. If this goes well, during commit time, we can just update all the records that were written and finally unlock them. So we see that software-distributed transactions are a multi-step process, and also records need to be augmented with some extra fields. We need a field to be able to lock the record during the validation phase. We need a version number to be able to detect conflicts between transactions. And we need a version for every single cast line of the record, so we know that while we are reading, no other write is interfering with our read. All this extra stuff causes inefficiencies in software protocols, and this is because of multiple implementation overheads. There is overhead for managing the read and write sets. There is overhead for updating the versions when we perform writes. There is overhead for checking read atomicity on reads. We cannot simply perform zero copy reads. We have to first read the record in a temporary variable, make sure that, okay, all the cast lines are indeed of the same version, or no write was interfering with me, and then store it in our actual variable. Operate at record granularity, so reads and writes fetch the whole records. And finally, there are additional RDMA requests for locking and unlocking records, poll for the completion of these lock operations, and rereading record versions to detect any conflicts between transactions. We evaluated these software overheads, and we find that they can account between 59 and 71% of the total execution time. So what we do in Reidys is that we take these software overheads, and we create an equivalent hardware mechanism that is trying to eliminate this overhead completely. So instead of having read and write sets, we have Bloom filters that sit next to the last level cache for local read and write requests, and in the NIC for remote read and write requests, where we record the addresses of the cache lines that were read or written during the transaction. Instead of updating record version for writes, we don't need any record version at all. Instead of checking for read atomicity, we're going to be using the Bloom filters to ensure the atomicity of reads and find out any conflicts between transactions. Instead of operating at record granularity, we can operate at cache line granularity now. And instead of doing logs and unlogs and rereading record versions to find conflicts, we will support some new messages that will offload these operations to the NIC. And then the NICs will be able to validate whether there was a conflict between transactions. And also we'll use the Bloom filters themselves to log the directory during the validation phase. So let's take a closer look to how these data structures actually look like. First, we enhance the directory in the cell LLC with an extra tag that is the write transaction ID tag. This means that when we write a cast line locally, we're going to tag this cast line in the LLC with the write transaction ID to let other transactions know that we have already written this cast line. If you try to access it, you have to squash. We also have some tags in the private caches that act as filters. So if the recorded read or write bit is set for a cache line, it means that, okay, you don't have to go to the last level cache and check. We have already checked for this cache line, so just perform the access from the private caches if you have. Otherwise, you have to go to the LLC and check if there is a conflict or not. We also have read and write Bloom filters next to the LLC that we record all the cache lines that were read or written during the transaction, and we tag these Bloom filters by the transaction ID. On the NIC, we have data structures for remote operations and for local operations that target remote nodes. For remote operations that target our node, we have read and write Bloom filters that record the cache line accesses that were happening from a remote node to our local node. And for local transactions, we have to keep track of some metadata, which are the nodes that participate in these remote transactions, and which are the cache lines that we are writing on remote nodes. So these are all the data structures that we have. And I'm going to try to explain that with an example. So imagine that we're executing a transaction, and then there is a remote read that is happening. We first send the request to the remote node. Then we add the addresses to the remote read Bloom filter. This is the Bloom filter that lives in the remote node's NIC. And finally, we fetch the data to the local node. A remote write works very similar. We send the request to the remote node. We add the addresses of the partially written cast lines to the remote write Bloom filter. We fetch the partially written lines to the local node. And then we buffer the updates of all addresses to the data structure that lives in our own NIC. A local read, it checks the directory tag to see if there is another transaction that wrote this line. And if it does, it means that there is a transaction conflict that we have to squash. If not, then we add the address to the local read Bloom filter. A local write still checks the tag to see if another transaction is writing the same cast line. It also checks the local read Bloom filters to see if another transaction has read this cast line before, so still this is a conflict. We have to squash the transaction. And finally, we add the address to the local write Bloom filter. So this is during the execution phase. Now, when we move to the validation and commit phase, there are operations that happen to the local node, and there are operations that are happening to the remote node. Everything starts from the local node when the transaction ends. So the first step is to lock the directory using the local read and write Bloom filters that are next to the LLC cache. So I'll show how this is done later, but this prevents other operations from touching the same cache lines that are members in these Bloom filters. Then we have to check for conflicts between the local writes that have happened to this node and all remote operations that are targeting the local node. So we're trying to detect conflicts between local and remote operations to the local node. If no conflict is detected, then an intention to commit message is being sent to all the remote nodes that participate in this transaction, alongside the updates that we're performing in these remote nodes. On the remote node, everything starts with getting the intention to commit message, and then it's locking the directory using the read and write Bloom filters that is storing in its own NIC for this transaction. After that, it needs to identify if there are any conflicts between the cast line that we are writing in this remote node and any other transaction. So it has to check with the Bloom filters that live in the NIC to find remote-to-remote conflicts on that node, and also with the Bloom filters that live in this remote node's last level cache. So to find any remote-to-local transactions that are happening on that remote node. If no conflict is filed with anything, then an acknowledgement message is sent back to the coordinator node. The coordinator receives all acknowledgements from all the different nodes, and then it sends a validation message saying that everything is fine, we can just commit the transaction now. So at this point, the updates can be performed, the Bloom filters will be cleared, and the directories will be unlocked. So partially locking the directory is a mechanism that we introduced to allow serialization of commits. So what we are doing here is that we go to the last level cache, and we enhance it by adding some Bloom filters in front of it. When an address where a memory request is trying to access this last level cache, we take its address, and while we are checking the tags to see if it is a hit or a miss, we are also checking for membership in these Bloom filters. If we find that this cache line is present in the Bloom filters, then we send the request back to be retried. We don't allow the request to proceed. Otherwise, it's a normal LLC operation where if it is a hit, it will just go to the LLC. If it is a miss, we'll send it to main memory. Besides Reidys, we have a hybrid approach to this protocol, where the goal is to minimize the processor changes. What if we try to put all the changes to the NIC as much as possible? So local operations will take the software approach for transactions, while remote operations will take the Reidys approach for the transactions. This means that hybrid Reidys utilizes the same NIC hardware exactly as the one we were showing before, and the only change that is needed on the processor is the partial locking of the directory using the Bloom filters. Okay. We evaluate our protocol against the baseline, which is the software implementation of transactional system. And we find that hybrid Reidys is 2.3 times faster than baseline, while Reidys is 2.7 times faster than baseline. This means that both of our approaches greatly increase the throughput, and we can see applications that have multiple small read and write requests to see even higher gains. This is because the software overheads of doing all this bookkeeping is further exacerbated for such applications. You can find many more details in the paper about how our design works and our implementation, as well as evaluation and multiple different results. But the conclusion is that Reidys utilizes hardware to alleviate the software overheads of distributed transactions. It achieves 2.7 times higher throughput than state-of-the-art software. And hybrid Reidys is an approach that keeps mostly unmodified the processor and achieve 2.3 times higher throughput than state-of-the-art software. So that concludes my presentation. Thank you, and I'll be happy to take any questions you have. Yeah.
Hello?
Yeah, it works.
Okay. So my question is, when you have multiple transactions at a node, then you need to order them, right? So do you use the logical clock to order them, or do you use some kind of physical clock to order them?
If I use the clock?
Clock.
No. So multiple transactions can happen on the same node. Each one will have its own data structures. All we need is a serialization point for the transactions. The serialization point for us is when they try to lock the directory, so only one is doing it at a time. So we cannot allow all the transactions simultaneously to go and lock the directory. This is the serialization point of our transactions. And that's the only thing we need to be able to say which transaction finished first, which transaction finished second.
So for distributed transaction, can you allow that to have multiple commit point? I can find offline.
Okay.
Shai from Google. Again, the question, how much software needs to change in order to use this?
Sorry?
How much does the software need to change in order to use this, in order to use Reidys?
So hopefully not much, because most of these operations will be supported through new instructions that we send to the RDMA, practically, new verbs. So it needs to change, but not drastically. They implement the core logic of the transaction doesn't need to change. It only needs to support the new operations so that we know that this has to be recorded in the Bloom filters. Now this is the transaction that ends. Everything else will be handled from the SmartNIC. It doesn't have to rewrite the whole application.
So just before I switch, I wonder, in the past, there were a lot of work on transactional memory, and we had the hope that this will solve the entire problem in parallel programming. Then it looks like that it vanished quite fast. What is the situation with transaction memory these days? Are people using it, or it's still academic work? Because in Intel they remove it.
So, I'm not representing Intel or the companies to know exactly who's using it.
I'm asking.
But there are processors that have HTM, and hopefully more will use it.
Okay. Thank you. So I'm sorry that we have short sessions, but maybe this is a good introduction to the BlitzCoin. Yeah. So the talk is Blitz as well. Please welcome Martin.
Thanks for introduction. So my name is Martin Cochet. I'm with IBM Research, and we'll be presenting BlitzCoin, a fully decentralized hardware power management for Accelerator-Rich systems on chip. So let's first go into a bit of motivation of a problem we are trying to solve. If we consider a large, highly heterogeneous system on chip with a wide variety of different accelerator tiles, we want to dynamically allocate a given power budget to each of the tiles based on each tile's activity and power profile while maintaining a global power cap at the SoC level. So this topic has often been discussed, especially in the case of large multi-core CPUs. However, for highly heterogeneous system on chips, we have several challenges that come up. First, we want this approach to be scalable to a large number of different tiles. We want to also have fine granularity both in space in time and the power levels to support the different tile profiles. This approach should also be workload agnostic, so that the algorithm can work on multiple different SoC configurations. And last, many fixed function tiles may not have the support to run an OS or software locally at the tile level. So the conventional approach is a centralized control where all the power management decisions are done by a single core, say at the center of the SoC. So this can give some flexibility, especially if implemented in software. But because the centralized controller needs to sequentially address all of the tiles, the response time of the power management grows linearly with the number of tiles. And last, the software's flexibility would come at the cost of much longer time scale of response time compared to a hardware solution. This is why we propose instead a decentralized power management, where all of the power management decisions are done as local exchange between neighboring tiles. This can result in a sublinear scaling of a response time and is easy to accommodate a wide variety of accelerators by adding a simple, small hardware component to each of them. However, one of the questions is how to make sure that this distributed exchange can enforce a global power target. So we'll here just briefly discuss the scaling trend of response time needed and provided by different power schemes. So if we consider a SoC with n tiles, which run n independent workload with an average duration TW, then on average there is an activity change at a time proportional to TW over n. That is, the maximum power management response time must follow that blue line. And conversely, we've said that centralized scheme, either in software with a red line or in hardware with the orange line, scale linearly with a number of cores. Note that the y-axis is in a log scale. Whereas, as we will see next, our proposed decentralized scheme scales roughly with the square root of n. Hence, if we look at the intersection of the different lines, we can see that, for example, fully centralized software scheme would only support about 10 core even for long workload, whereas our scheme can scale to up to 100 plus workload, even for up to 100 plus tiles, even for very short workloads. So let's see now in a bit more detail how is BlitzCoin working. So the general idea is to represent our power budget as quantized unit of power that we call coins. Then each tile will exchange coins with its neighbors. And then, based on its current coin allocation, we'll use a per tile DVFS scheme to adjust its power. So here is how it's done in a bit more detail. So in this example of a 3x3 SoC, each tile has a coin target max and a current availability has. So then, for example, the center tile will send a message to its neighbor, left neighbor, say I have 3 coins, I will need 8. Based on this, the neighbor will give 5 coins back to the center tile. And this exchange keeps happening in parallel across all the different tiles, leading to a global convergence where all the tiles have the same has to max coin ratio. So we want to first validate how this response time of the power management scales with a number of cores n. And through emulation, we found that if we see this graph, where we show on the x-axis the square root of a number of tiles n, and on the y-axis in the solid line the response time, that we have heuristically found that the response time scale with the square root of a number of tiles, which is a very significant improvement compared to centralized schemes, which, as discussed before, scale linearly with a number of tiles. We use this model to add a couple of improvements to our previously described coin exchange scheme. First, we do some exponential backoff to dynamically adjust the exchange rate based on the SoC activity, which helps speeding up response time and reducing knock traffic. And finally, we use some occasional random pairing, where a tile would exchange coin not just with its neighbor, but with tiles that are further away. And as seen on the histogram below, the random pairing helps alleviating convergence to a local minimum and guarantees in this Monte Carlo simulation that with random pairing, all of the exchange converges to the ideal target within the coin quantization limit. So let's see now how BlitzCoin is implemented in hardware. So we have our SoCs partitioned into multiple tiles, with one tile shown here. So the tile includes a global domain in blue, the NOC domain, which is shared between all of the tiles, we have the same domain, and in green, a per tile domain where the voltage and frequency is scaled. So first, those tiles are composed using the ESP framework, which provides NOC communication between the tile where the coins are exchanged. Secondly, once a tile receives its coin allocation for exchanges, we have a BlitzCoin FSM, which performs the coin exchange algorithm described previously. So third, we have a lookup table which converts the coin allocation, that is the power target, into a frequency target. And this lookup table is pre-filled and characterized depending on each specific accelerator power profile. And last, we have a unified voltage and frequency feedback loop, which will adjust the tile domain voltage and frequency to match this power and frequency target. So there's more detail on the VFR on our companion paper that we published at VLSI this year. So now, how did we evaluate BlitzCoin? So we've implemented it into 3 different SoCs. The first two on the left, a 3x3 and 4x4, targeting 2 different implications, were validated at the RTL level on a 12 nanometer process, while on the right you can see a fully fabricated and measured SoC, also including BlitzCoin for the 10 center tile marked in orange. This was all done thanks to ESP, which provides a very straightforward methodology for composing those different SoCs. As you see here, we've kept the focus on BlitzCoin on the accelerator tiles that represent most of the power consumption. We're comparing our scheme BlitzCoin with a centralized implementation of it, BCC, which run on the CPU tile, and a centralized round-robin scheme, CRR, derived from a previous work. As you'll see next, we're evaluating BlitzCoin on both fully parallel workload as well as more complex dependent ones. So if we move to the next slide, we'll see now RTL level evaluated results of BlitzCoin in that 3x3 SoC. So we see here on this graph on the x-axis the time during the workload execution, and in the 6 different colors the power during the runtime of the different accelerators. Here are shown our 2 baseline BCC and CRR, which do enforce our power target cap of 120 milliwatt. But if you see on the zoom-ins, the response time is pretty slow in the order of 10 plus microseconds, which means that the SoC doesn't always take advantage of the full power available. In comparison, BlitzCoin, thanks to the distributed and hardware implementation, has a sub-microsecond response time, and hence, as you can see over time, really fully takes advantage of the available power cap. And this translates into a much faster workload execution as well. So this was for one example of 3x3 SoC. And so we've performed similar experiment on the 3x3 and 4x4 SoC and both parallel and dependent workloads. And we've seen all those cases about 25 to 34% speed up compared to CRR baseline, and on average 8 to 10x faster response time of BlitzCoin, which will be very important for scaling to large SoCs. So now let's look at the third SoC, which this time was fully implemented in hardware, which is very important when we have here a system that relies on multiple tile interaction as well as mixed signal voltage and frequency actuation within the tile. So this is a 12 nanometer, 64 square millimeter SoC with 10 tiles with NVDLA, Viterbi, and FFT accelerators with BlitzCoin enabled. So we first look at the graph on the top when we have the lab measured power trace in blue of BlitzCoin compared in orange with a baseline where the power is statically allocated. And we see that BlitzCoin provides about 27% throughput improvement. We are also able to measure in silicon the coin exchange, as seen on the graph of the bottom left, where at the end of the NVDLA workload, the power is the tiles, the other tiles receive the coins after about 0.68 microseconds. And last, you can see a measured scope illustrating the example of a dynamic voltage and frequency scaling. Okay, perfect. So we see last how we can scale those results to larger SoCs. So if you remember one of the first slides, for centralized scheme, the maximum number of tiles that can be handled grows proportional to the workload duration to the power of 1/2, whereas through BlitzCoin, because of the distributed exchange, we have a faster scaling. Hence, we can scale up the results and see for different workload what is the maximum number of tiles that can be accommodated with this power scheme. And we can see that BlitzCoin supports about 3 to 13x larger SoCs compared to BCC, CRR, as well as 2 other works from the literature. Okay, so now to conclude, BlitzCoin is the first fully decentralized hardware power management scheme. It is specifically tailored for large heterogeneous system on chips. Thanks to the distributed nature, we have a sublinear scaling with a number of cores. This has been fully proven in a 12-nanometer taped-out SoC, and we show about up to like 13x larger scaling compared to previous hard schemes. And last, BlitzCoin has been released as part of the ESP, so you're welcome to check it out on your own. Perfect. That's all. Thank you.
Joseph Torrellas from Illinois. I'm not sure I understand the rationale for this distributed synchronization to change the voltage. And is it really scalable? How does it compare to a hierarchical mode, where as you increase the number of cores, you would be, in a modular manner, increase the levels of the hierarchy?
Yeah, that is a good question. Modular hierarchical approach has been done in prior art and works usually pretty well for like mostly homogeneous systems that can easily be partitioned to hierarchy. But our goal was to be able to accommodate any like highly heterogeneous SoC which could have a wide variety of accelerators, in which case there may not be an obvious way of building such a hierarchy. This is why we wanted to do a fully flat approach to like have it be generalized to any like heterogeneous system.
And it scales to a large number of
Exactly,
cores?
that's the idea, that the response time does scale like sublinearly compared to a centralized scheme. So that's the key idea here.
Thank you.
I just wonder if you can put your computer. If you use separate power plan, so it looks like that you can change the voltage asynchronously, and you don't need to have a global FDFS.
Yeah, exactly. I think the idea here was to have this global domain for communication.
I know, but in large system, usually you cannot, and it is not efficient to have a global power plan. Anyhow, it is much more efficient to break it into local power plants, and then you can change each one of these power plants independently, and you don't need to have decentralized.
Okay. Yeah, I think here only the communication is asynchronous when we have a pair tile and asynchronous boundary between each tile. So that is the idea here.
Okay.
Thanks.
Thank you.
Thanks.
Okay. The next talk is Mad Max. So, Samuel Hasia.
Close enough.
Yeah. Oh, sorry for the. So, please introduce it and the floor is yours.
Okay. I'm using this mic, I think. Okay. Let's do it. Okay. Thank you, Avi. So I'm Sam. Today I want to talk about Mad Max. It's a performance model for distributed ML that we worked on recently. But what I really want us to think about are the challenges behind mapping complex models into physical space, and the important role that cross-stack performance models can play in finding solutions. So let's take a 30,000-foot view of the problem. So while we already know the obligatory models are getting a larger piece, the complementary fact is that the systems that we map these models onto are also increasing in size and complexity. So this really makes the mapping process that much harder, and it leaves a lot of efficiency on the table when we choose suboptimal parallelization strategies. So with MadMax, we introduced a validated performance model that is helpful across the algorithm system stack for finding the right mapping strategies. So if I still have your attention, I'll go over this talk. So in this talk, we first go over the background motivation, including taking a peek under the hood of Meta's production GPU clusters. Then we go over the MadMax performance model itself, so the design, the validation, and last but not least, we go over the use cases and try to see how MadMax can identify some trends and design recommendations. So background and motivation. So one way to think about the model side of this equation is we can think of models as a sequence of layers, where the layers themselves can be quite different in nature. So you can think of like attention layers, embedding layers, and so forth. And from the physical space side, you can think of devices and nodes, where nodes are composed of devices. And we usually think of devices as like GPUs and nodes as like the idea of like DGX boxes and so forth. So in production, the reason why this is challenging is that the nodes, they can be on the order of hundreds, or as we're seeing now, also in the scale of thousands. And as I said earlier, this mapping problem is quite complex for two reasons. Number one, each layer, they can have its own parallelization strategy. So in this paper, we like look into popular ones that, such as like distributed data parallel, tensor parallel, fully sharded data parallel, and so forth. And we also look into hierarchical versions of these. And the second reason is that the right strategy, it'll depend on the system's capabilities and also the interactions between the algorithms and systems. So what these two observations really reflect is the reality that finding the correct way to map models onto physical space is inherently hard. So what does correct mapping look like? For a training experiment, for example, we care about two things. We want to train as fast as possible, and while we also want to reduce cost. So if we use like industry standard default parallelization strategies, each hardware, you can see it'll give you like each hardware networking configuration, it gives you a distinct training time and cost. With successful mapping, we want to push this frontier forward to train faster and cheaper. So as mentioned earlier, one of the hardest challenges in this space is the heterogeneity across both algorithms and systems. So understanding this heterogeneity is crucial in finding the right mapping strategy. Across the algorithms, we have a mixture of large ML models of different sizes and shapes. Across the systems, we have clusters that differ in the core accelerator, networking specifications, and scale. So as you can imagine, this introduces cross products of heterogeneity that make it really hard to figure out what is the best mapping strategy. So simultaneously, we're trying to figure out what are the model cluster interactions and how do we actually do the mapping. And in reality, we already see this diversity seep into Meta's data centers. So this is what was recorded like in a time length of like a quarter last year. So we can kind of see, okay, across these two different types of models, like recommendation models, denoted as DLRM and LLMs, there's some of the emphasis is on communicating embeddings, while others are on compute for attention layers and MLP layers. And we see something similar for communication collectives as well, where we see there's lots of diversity. And the point I want to get across here is, with all these different communication collectives, with different emphases, they stress different hierarchies of interconnect. So there's a lot of diversity here as well. So how do we actually do the mapping like right now? So we tend to think of there are three different ways to go about it. Number one is to use like an industry standard strategy such as FSDP. And the drawback of this is the results you get aren't performance optimal because you're really trying to target something that's in terms of feasibility. And second is you can engineer model-specific solutions. The drawback is like it requires a lot of time and heavy engineering effort. And the dirty secret is that it takes a lot of expertise to figure out what's the right strategy to use. And last, like there's a lot of research tools out there, but in our experience, some of the insights don't really fully carry over, or they aren't sufficiently validated. So this motivates why we need a quick performance model to evaluate this design space. So next I'd like to talk about MadMax, the model design and validation. So MadMax itself is a couple steps of a performance model, and it's quite, I'd say, straightforward. So first you want to specify the model architecture and task. So here we have some kind of recommendation model that has a transformer component in it as well. Next, you want to specify how you want to cut the model up, and you can do the specification by the layer type. So as I said earlier, there's different parallelization strategies you can use. Third, you want to specify the order in which you execute the layers. Fourth, you want to process the individual layers and generate traces for each layer. And last but not least, you want to piece together the traces so that you can get a full complete picture of the compute and communication required to execute this model with the parallelization. So yeah, so the next thing, as you can kind of see, the key to this are GPU traces. So you can kind of see with these building blocks, there's a lot of information from these traces that we can use. And you can have insights into bottlenecks, right? So based on how these traces are connected, you can kind of see, oh, there's an area of exposed communication and so forth. And MadMax also has some basic visualization tool as well. But what we get from this is, the key insight is, what we believe in is, if you can emulate GPU traces behavior closely enough, you can kind of get a sense of how things will actually run. So put the design aside, in order for the model to be actually useful, it really has to be validated. That is, what MadMax predicts has to closely follow real GPU execution. So here we show one of our validation efforts for training a production recommendation model on 128 GPUs. We validate serialized execution, and this is important because we want to make sure the raw volume of compute and communication matches. And we also validate overlapped execution, which is important because we want to see if things happen in the right order for both compute and communication streams. So in the paper, we show more validation case studies across different model architectures and distributed systems. So this boosts our confidence in MadMax across different large-scale ML use cases. So now that we've gone over what MadMax looks like and the validation, some of the highlights of validation that we've done, I'd like to go over some of the use cases of MadMax. So in the paper, we look at a bunch of use cases across model architectures, systems, and deployment scenarios. We believe that these insights demonstrate how extensible MadMax can be. In the interest of time, we will go over 3 case studies today. So the first one is about identifying, as I said earlier, optimal parallelization strategies. So we can kind of see over here, there's a bunch of different types of models. There's recommendation models and their variants, so transformer style, mixture of expert style recommendation models, and different classes of recommendation models, and also LLMs and variants of LLMs, such as mixture of expert style LLMs. And what we want to identify here is, compared to using a standard like FSDP as baseline, how much better can we improve training throughput? And the answer is we can find strategies that will give us improvement. And what I really find interesting is that, like, besides the numbers here, is that the optimal parallelization strategy, it varies by the model architecture. So there's not really like a one-size-fits-all solution here. And additionally, for models like the DLRM transformers, the parallelization strategy also differs based on your layer type as well. So, and since MadMax is a performance model, we can also explore potential gains from relaxing memory footprint constraints. The next case study that we want to look into is designing new hardware. So the question that we want to ask here is, what happens when you're not constrained by the already given GPU specifications? So we want to think about, hey, what happens if we scale compute, memory capacity, bandwidth, interconnect bandwidth at both the intranode, so like NVLink, or internode levels, such as scaling up InfiniBand and so forth. So first we can kind of see, okay, blue shows us if we just play around with parallelization strategy, which is what we showed earlier, you get some gains. But MadMax allows us to see new hardware designs where if we scale just purely compute, peak compute, or memory capacity, what is the impact of this on a pre-training task or an inference task? Likewise, we can see for different things as well, such as for memory bandwidth and interconnect bandwidth. So in this case, we see that for this recommendation model, training inference, interconnect bandwidth is crucial for, since this workload is communication dominated. And also, like, we can, play with different ratios and see how if all of these scaling things come together, what is the improvement? So the last use case I want to show is like thinking about cloud instances. So we're thinking about stuff like AWS, Azure, GCP, stuff that's like really popular out there. So, and the interesting thing is there's a bunch of different configurations. Even if you have the same GPU, you have different interconnect configurations. And optimally, we want to train, again, we want to train as fast as possible and take the least amount of money. So each data point here is a public cloud GPU instance with a base parallelization scheme. So using the standard like FSDP, you get a data point for each. And with MadMax, we're able to identify parallelization strategies and specific for different configurations that push the envelope of faster and cheaper training. So that pretty much concludes this talk. But what I want us to take away from this talk is that as models get larger and more complex, the task of mapping them to physical space gets harder and requires more insights from across the stack. This is where tools like MadMax comes in. It helps us build better insights for better mapping strategies. So for more in-depth characterization, or more in-depth discussions on data center scale characterizations, alternative case studies, and instructions on how to set up and run MadMax for yourself, please check out the paper. Thank you.
Any question? One question, I just wonder how you estimate power. Performance is quite clear, but can you do something similar to power impact of DVFS, etc.?
No, Avi, that's a great question. So the question is we looked at performance, but what about other aspects like power, right? So I think the challenge with power is we can get numbers on GPU powers, but also there's also a lot of I guess the CPU side and the networking stack, I guess we'd have to think about how when we have overlapping components, what's the right way not to overcount power and so forth. So that's still an ongoing problem. But I think the power side is definitely harder to estimate and think about than the performance side. But that's a good question, yeah.
Yeah, okay. Any other question? Okay, let's thank the speaker. And the last talk in this session will be about virtualization. So it doesn't matter what we are doing, we're still in ISCA 2024. Okay. So let's so this talk is about efficient virtual memory translation for multi-chip model from the Feng will present it. You're from University of California?
Yeah.
No, actually.
Yeah, I use that. Yeah, thank you. Hi, everyone. I'm Feng. I'm a PhD student from UC Merced. Today, I will present our work, backward efficient virtual memory translation for multi-chip module GPUs. This is a collaboration work between UC Merced and Georgia Tech. Recent emerging applications like deep learning require tremendously large memory and compute capacities. Due to its superior performance, GPUs are the de facto standard accelerator for those applications. While the application keeps scaling up, it is really hard for a single die GPU to catch up the trend as the chip yield decreases. Therefore, GPU vendors choose to produce multi-chip module GPUs or MCM GPUs. However, it is quite challenging to manage those ever-large resources provided by MCM. Mechanisms like smart page migration and allocations are intensively studied, and such techniques heavily rely on virtual memory. But is a traditional virtual memory efficient enough for such novel MCM GPU architecture? Before jumping to our idea, let me firstly describe the MCM GPU based on the architecture that we target at. we consider a single GPU package that connects to a host CPU via PCIe. The GPU package contains multiple GPU triplets, and here in this figure, there are 4 GPU triplets. And each GPU chip is a fully functional GPU. It is equipped with L1, L2 caches, L1, L2 TLBs, and also each GPU triplet has its own dedicated DRAM. Those GPU chips are connected via high bandwidth interconnections. So based on the baseline architecture, now we discuss what is the performance impact of virtual memory translation in MCM GPUs. Here in this figure, we demonstrate the performance with 8, 16, 32, and infinite number of page table workers with 19 GPU applications. From the experiments, we see almost linear speedup every time we double the number of page table workers, while it's saturated at 2x. This reveals that the virtual memory translation is a new bottleneck and requires a fundamental revisit for MCM GPUs. Then one may ask, can existing conventional techniques and wisdom solve the problem? We firstly evaluate the superpage solution by enabling 2 megabyte paging. Results shows that such coarse-grained management will result in actual page migration overhead and sometimes harm the performance. We then evaluate the TLB prefetching solution. Here in this figure, we present the page translation stride of adjacent requests. Conventional prefetching rely on next page access or stable strided access. However, we find that if we change from a hypothetical monolithic shared L2 TLB to an MCM setting, the stride is much more diverse and unstable. Finally, there are recent work target multi-GPU cluster and propose to share the L2 TLB entries between GPUs. However, we find that under an MCM setting, the exact TLB sharing happens infrequently. In this figure, we show a hypothetical architecture that share L2 TLB among different GPU chiplets. The result shows that such hypothetical setting only bring marginal performance benefit. So motivated by the previous analysis, our goal is to provide an efficient virtual memory translation specifically designed for MCM GPUs. Our key insight is that memory allocation itself among different GPU chiplets can provide actual hints for efficient memory translation. Our idea is to leverage them and provide it to Kokolis address translation from different GPU chiplets. We firstly explore how centralized IOMMU can leverage the structural page placement. We call it bar. We then explore how such hints can be shared and leveraged within the GPU package. We call it full bar, and together we call it barcode. Now let's discuss how pages are allocated in MCM GPUs. On the left-hand side, it is a simple GPU program that contains 1 GPU kernel and 3 relevant data. So firstly, a kernel just-in-time compiler analysis is performed to analyze the access pattern within the GPU kernel. This is done by following some existing works. Then after we capture the locality at runtime, the GPU malloc driver call is evoked. By following the locality, data are allocated. Here, 12 pages are allocated to data 1, and 4 data are allocated to data 2, and 3 data pages are allocated to data 3. But since there's no rule, the page can be placed at any possible locations in the system. Therefore, the page table walk is needed for every single page upon L2 TLB misses. We then introduce our key idea coalescing group. The idea is to provide a lightweight page allocation rule by mapping pages of the same data on the same physical location addresses. Here, we intentionally enforce the same relative page to be allocated at same physical locations. For example, pages 01, DX1, DX4, DX7, and DXA are allocated at physical location 0x0075 at each GPU chip. And similarly, we can process data 2 and data 3. We call those page groups that we enforce to locate at the same physical location as a coalescing group. And because they are at the same physical location, we can infer the other 3 addresses whenever we finish translating any one of them. Now let's see how such coalescing scheme can benefit the performance. In the baseline architecture, to translate all 19 pages, by assuming L2 TLB misses, it requires all 19 page table walks. However, with bar, when we finish one translation, we can check the page walking queue and find if there's any translation requested waiting in the queue that in the same coalescing group and can be inferred without a page table walk. Overall, with bar, we are able to finish the same translation request with only 7 page table walks. So even though the coalescing group can potentially bring huge performance benefit, recording the coalescing metadata can bring huge overhead. Here we propose to encode the coalescing group metadata into unused bit in PTEs. Here, let's take PTE 0x4 as an example. In the baseline x86 PTE, there are 11 bits remain unused. So for the first 8 bits, we use them to store the validation information within the coalescing group. We call it coalescing bitmap. And for the rest 3 bits, we use them to store the rank information of that specific PTE within the coalescing group. For example, for PTE 0x4, the binary 1111000, it means that the first 4 GPU chips have a valid PTEs in the coalescing group. And binary 001 means numerical value 1. It means the page number 1 in the coalescing group. It is the page number 1 in the coalescing group. Then let's discuss how we decode the coalescing information from the PTE and how such information can be used. Here on the right-hand side, we propose a dedicated buffer and logic to store the data object's metadata we call PC buffer. The PC buffer has 4 fields, the starting and end VPN, and the interleaving granularity. And last field is called GPU map that record how logical GPU chiplet ID is mapped to physical ones. We then demonstrate an example that by starting from a translated PTE 0x4, and we translate a VPN 0xa. Firstly, we check the start and end VPN of 2 PTEs and verify that they are in the same data range. Then we find that by adding the interleaving granularity, which is 2 times, we know that 0x4 and 0xa are in the same coalescing group. Then, since the multiplier integer is 2, we know that 0xa is 2 GPU away from 0x4. And then, since 0x4 is a translated PTE and located at GPU 1, we know that 0xa is located at GPU 3. Finally, since 0x4 is a translated PTE, we know that PFN of it is 0xb075. By minusing the base address of GPU 1 and add the base address of GPU 3, you can finish the translation with simple calculation for VPN 0xa without page table work. Well, bar is able to coalesce page table that located at the page table queue and therefore boost the performance. There are still room to improve. Firstly, the GPU address are still translated in centralized IOMMU via slow PCIe. To solve this, we propose intra-GPU translation to keep the coalescing and translation within the GPU package. Secondly, the coalescing group size is limited by the number of GPU chips that in the system. This limits the potential performance benefit. To address this, we propose contiguity-aware coalescing group expansion. Thirdly, the coalescing oblivious pagework scheduling limits the opportunity of coalescing PFNs. To address this, we propose coalescing-aware page table work scheduling. Baseline bar enhanced with those 3 optimizations is called full bar or F bar. In this talk, I will cover the first 2 optimizations. Please check out paper for the third one. Now I introduce our first optimization, intra-GPU translation. The idea is to share the coalescing information among GPU chiplets. Here, we integrate 1 PC logic and 2 cuckoo filters per GPU chips. One is called remote coalescing filter that is used to tell which remote GPU chiplet may contain the coalescing group that contains the requested translation. And the other one is called local coalescing filter, which is used to predict whether local GPU contains the coalescing information that remote GPU asks for to avoid exhaustive search. Operational-wise, we firstly check RCF to get the potential GPU chip that contains the translation. Then it will send the request. Then the remote GPU will query its LCF and check L2 TLB and find if all of them return a hit, a translation result will be returned without a page table work. In baseline bar, we are able to coalesce multiple GPU requests in the same coalescing group, but only at LMMU. With the proposed intra-GPU translation scheme, we are able to share the coalescing information among GPU chiplets and share it within the GPU package. Therefore, a coalescing group that has been translated by one can be leveraged and serve translation for the others. PTEs in bottom is translated without going to LMMU, and the performance is therefore further boosted. The second limitation of baseline bar is the coalescing group size is limited by the number of GPU chips in the system. Our solution is called contiguity-aware coalescing group expansion. The key idea is to opportunistically expanding the coalescing group whenever memory allocation is observed. Here, suppose that we're still trying to allocate 12 pages and for 1 data object, but while we're constructing coalescing group, the driver can find if there is contiguity-aware available to explore. Then FR is able to expand those 2 contiguous coalescing group into 1 and enlarge the coalescing size. Here, to support the expanded coalescing group, we also further modify the barcode PTE to encode the merging information. Optional-wise, without contiguity-aware coalescing expansion, the coalescing group size is limited by the number of chips. In this example, 1 page table can only cover up to 4 PTEs. With contiguity-aware FBAR, we merge coalescing group information. Therefore, the X5, the X2, the XB, the X8 can be translated alongside with the XA. The performance is therefore further boosted because with larger coalescing group, because one page table can cover up to 8 PTEs. So for evaluation, we use 7-level simulator and GPU sim to conduct the experiments. We model a GCN3 like AMD GPU, and each GPU package contains 4 GPU chiplets. GPU chiplets are connected via 768 Gbps interconnections. We model CPU-GPU connection similar to PCIe Gen 4 X16. We model LMMU to have 16 page table workers and 48 page table queue in the system. For overall performance, we compare against baseline architecture and 2 state-of-the-art work. On average, full bar code is able to achieve 1.36 speed up over SOTA work on average. If we opportunistically merge 4 cores in group, bar code is able to provide 1.43 more speed up. Such a noticeable performance benefit is because bar code can fundamentally remove expensive page table works. In this figure, I present the performance benefit under different number of GPU chiplets. Overall, when there are more GPU chiplets in the system, bar code is able to construct even larger coalescing group, and the performance benefit is therefore even larger. So we have much more detailed evaluation, like breakdowns, GPU MMUs, super pages, and much more. Please check our paper for more detail. Thank you.
Thank you very much.
Hello, so I have one question. How is this different from huge pages? So instead of like allocating across GPUs, like allocating one in here, and also how you deal with fragmentation.
Can you repeat your second question?
Fragmentation, how you deal with fragmentation.
Oh yeah, that's a very good, this is pretty much like a single but two like variants of the same problem. So the difference between this one of the bar core and superpage is because that superpage, firstly, like it needs to find like physically contiguous space to allocate one huge page or superpage. But well, we don't need to do that.
But don't you need contiguous in across these?
Yeah, crosswise, but there are more opportunity to find those other than like single chip within the contiguous space. There are more opportunity we can find those, and therefore the fragmentation is less frequent. Thank you.
Thanks a lot for the download.